Hello, my name is Aman Patel, and I want to thank you for taking time out of your day to view this recording. My partner Kasamwani and I will discuss our final smart home project. Smart home is a rapidly growing industry. It gives its consumers the ability to control the systems within their homes through automation, whether it be from their phones, computers, and even virtual assistants like Google Home and Alexa. In addition, companies such as Ring are also widely popular within this industry. As discussed in the previous slide, the opportunities within this industry are limitless, which is why Qasim and I chose to create an automated smart home system. This project is providing us with great real-world experience. Our smart home system will be on the 16 by 2 LCD display and have Android app compatibility through Bluetooth. Specifically, our system will have these basic functional capabilities. As stated earlier, it will be compatible with the Android app that we have built from scratch, control appliances through the Android app, such as turn on or off based on the threshold temperature that we set, deliver audio messages during critical situations, such as when an intruder is breaking into the house, automated night light system, which turns on the lights or off based on the time of the day, have an intruder system which is capable of sending audio and mobile alerts, and at last have a weather system that can read and display temperature on the LCD display and the app.
Bro, fuck you, man. Come on.
What you could have done? We were just
No.
looking at what you were doing.
Just close it. How am I supposed to record? I have an hour left.
Record now. Okay.
But after an hour, literally.
Hello, my name is Aman Patel, and I want to thank you for taking time out of your day to view this recording. My partner Kasamwani and I will discuss our final smart home project. Hello, my name is Aman Patel, and I want to thank you for taking time out of your day to view this recording. My partner Kasamwani and I will discuss our final smart home project. Smart home is a rapidly growing industry. It gives its consumers the ability to control the systems within their homes through automation, whether it be from their phones, computers, and even virtual assistants like Google Home and Alexa. In addition, companies such as Ring are also widely popular within this industry. As discussed in the previous slide, the opportunities within this industry are limitless, which is why Qasim and I chose to create an automated smart home system. This project is providing us with great real-world experience. Our smart home system will be on the 16 by 2 LCD display and have Android app compatibility through Bluetooth. Specifically, our system will have these basic functional capabilities. As stated earlier, it will be compatible with the Android app that we have built from scratch, control appliances through the Android app, such as turn on or off based on the threshold temperature that we set, deliver audio messages during critical situations, such as when an intruder is breaking into the house, automated night light system, which turns on the lights or off based on the time of the day, have an intruder system which is capable of sending audio and mobile alerts, and at last have a weather system that can read and display temperature on the LCD display and the app.
So, we're well aware of the current crisis the world is in, and to take a proactive action in addressing COVID-19, I have been working for the past 5 weeks on developing Preventiv, a free contact tracing app for COVID-19. To further understand on how Preventiv works, Qasim will demonstrate a brief 28-minute video explanation on how Preventiv functions.
Now I will discuss the overall approach that was used to complete the project. First, we utilized the Agile method, which focused on us testing and building each individual circuit and then slowly integrating them one by one. Kotlin was used to build the Preventiv app, while Java was used to build the smart home app. As to satisfy the audio message requirement, the audio amplifier circuit was built in two designs. The first design focused on using the LM386, which is the final design that we chose on due to time constraint, and the other design that was used focused on building the same essential circuit but replacing the LM386 with resistors, capacitors, and transistors.
Smart Home 3.0 has the following main features. Appliance 1 signaled by LED 1 of color red biased by a 480 ohm resistor. LED 2 as appliance number 2, also biased by a 480 ohm resistor of color green. A fan not biased at all, signaling as part of the weather station. An LCD screen display as part of the weather station, producing real-time temperature and humidity, relative humidity updates. An LDR system where the output is an LED night light turning on when it's too dark, signaled by a green LED, not biased, for maximum effects. A buzzer system controlled as part of the intruder alert, where the output is an audio amplifier controlled by an LM386 module, which produces a 30-second clip of a police siren noise. And last but not the least, a Raspberry Pi camera system for security camera. And lastly, the DHT11 humidity and temperature sensor for producing data for humidity and temperature onto the LCD screen and the app. And all of this is controlled by a Raspberry Pi 4, while as the audio amplifier is powered up by an Arduino Uno 5-volt source as the Pi itself.
So let's talk in details about the first appliance. Well, we considered to choose to use LEDs as our appliances 1 and 2 respectively. We chose LEDs of different colors and we biased them off by a 470 ohm resistor given by the mesh current equation. And we used different GPIO pins to represent different LEDs to turn on when a specific signal was fed into the input by the app itself. So how does it actually work? Well, what happens is as soon as you go onto the app, as you will see momentarily in the video, a request is sent to the server, an Apache server hosted by Raspberry Pi, and that server will constantly look for new URLs that the app is requesting for. And as soon as the app sends in a specific URL to the app, the Apache server has a built-in PHP script that was coded, and that PHP script performs any of the following actions depending upon the specific hash value or the key value pair from the app itself. One of the functions that the app can perform is turning on an LED, such as appliance 1 or appliance 2, or turning on or off the fan itself. And all of this is done by controlling the app by signaling a specific command to the app to the Apache server hosted by Raspberry Pi, which controls a PHP script, which then executes a batch file or an executable controlling a specific function of the wiring Pi API for controlling a GPIO pin input or output command, such as turning on an LED or the fan itself, given by its wiring of the GPIO. And that is done through the wiring Pi API. And let's watch the video on how this works. So in here, I'm just turned on my phone and went to the app, and as I click on, you can see LED 2 light up. And similarly, as I click LED 1 switch on the app, it lights up. And you can notice how seamlessly this whole transition is being processed. And this is done without using Bluetooth configuration. It's done on Wi-Fi because it provides for a wider range since you're on the same network at all times, which makes more sense logically instead of using Bluetooth, which I believe was an incorrect decision made by the course designers to choose to use Bluetooth or Wi-Fi. And as you can see here, fan being turned on and off too by the app itself. It's a very seamless and minimal delay application. So let's talk about our next application feature, the LDR system. The LDR system, or the light deterministic resistance-based system, is based upon three main components: an A to DC converter, a photocell resistor, and the output produced by an LED. Well, what happens is the following. Let's say it's dark. Our smart home automatically turns on an LED in case it gets too dark, and it turns off that LED in case it's not too dark. And the way it works is based on the following principle. As bright light shines on the photocell resistor, and if the amount that the bright light shining on the photocell resistor reaches beyond a certain particular threshold, the LED will light up, and vice versa if there's minimal amount of sunlight or photons. So why did we choose to use a capacitor? Well, that is based on the following principle. As the capacitor gradually charges up, this is due to the fact that the system is powered up by the 5-volt output source from the Pi itself, the voltage that passes through the circuit and to the GPIO pin rises gradually. Now, as a capacitor charges up to a certain point, its voltage rises roughly about 2 to 2.5 volts, and this whole gradual rise is sensed upon the Raspberry Pi's GPIO pin 13, as that was the pin that was chosen as part of the LDR system. If the resistance of the sensor, the photocell sensor, increases, the capacitor will now charge up at a slower rate, and therefore the circuit will now take an elongated period of time to reach that same amount of voltage of around 2 to 3 volts. And all of this is done by this implementation of an A to DC converter. Instead of using one, we chose to use a capacitor to represent it. The capacitor essentially measures how many cycles in the processor does the processor take to reach up to a point when the capacitor is fully charged. And that is our reference voltage threshold point. And based on that, if it hits a certain mark, which we define as 25,000 cycles, that means that it's too bright and therefore, that means it's too dark and therefore the capacitor, the LED should light up. Now, if it's less than 25,000, which we set as a base threshold for the cycle in the concurrent processor, then LED should not light up. And that is the premise of our night light setup. Now, let's demonstrate that in the video shown here. So as you can see, the closer I bring my palm towards the photocell resistor by trying to create darkness, the more likely it is that the LED will light up. Now, let's talk about our unique implementation of the weather station. We believe that our weather station should not only receive commands such as the current temperature and humidity, but also be an active member in releasing energy or either increasing or decreasing the temperature as per the user's desire. Our weather station is built upon two parts, a passive user experience and an active user experience. Our passive user experience basically does the following. A master unit which measures the current temperature and humidity and displays on a 16:2 LCD display, and a slave unit which is being controlled by the app on turning on and off the fan at the user's discretion. Now, going to the passive unit, this whole system is based upon the same feature of an LCD screen as the unit that displays temperature and humidity, but also if the temperature reaches above 26 degrees Celsius, the fan will automatically turn on. Now, the LCD screen is a 16:2 screen whose pinout configuration can be shown in the image to your right. In particular, we use the following connections. The RS pin was given a GPIO pin 26. The enable pin was set out as GPIO pin 19. The four data pins that we chose to use were D4 through D7 in the following order: GPIO pin 13, 6, 5, and 11. We set out our contrast by the potentiometer for variable resistance instead of maximum contrast, as that is not shown in the schematic. We also implemented a unique implementation of the intruder alert system. The alert system is built upon two major components: an input source, in this case a push button, two output sources. The first, an LED turning on when the button is pushed, and the audio amplifier producing a 30-second audio sample of a dot wave file of a police siren. We also implemented a ring-based security camera setup for accessing your outdoor activity that can be shown in the next slide. But first, let's watch the audio amplifier in tandem with the push button. In this video, you will observe that when the push button is pressed, the LM386 module and the audio amplifier will help produce a 30-second clip of a siren. And you will also notice that during this time, the yellow LED will light up. Let's watch it. This part of the video shows how I incorporated a ring-based security camera implementation using Raspberry Pi 4's built-in camera module through the terminal. In this video, you will observe that I am accessing a live network stream of my Raspberry Pi camera's output on a remote phone connected to the same network. This is of particular value when you are trying to see who is outside your house knocking on your door, or if you want any CCTV-based surveillance approach where you have access to the live footage at any given point of time. Let's watch this video. In here, you can see me live streaming from the camera and the output being displayed on the cell phone on the table. As my face with great mustache and beard is shown with a terrible pun on the t-shirt, you can identify that that has been displayed from that camera as pointed by my palm. And as I block that camera, notice that there was a visible delay, which was not shown, but was evident. Now, let's talk about the audio amplifier design in great details. Aman, why don't you take the stage and set it up for us?
As stated earlier in the video, the audio amplifier had two designs. The initial design, which is the LM386, was chosen to be the final design. Here, as you can see, on the bottom right is the schematic for this LM386 design, which was taken from circuitbasics.com. The battery, as seen in the schematic, was replaced with the Arduino Uno to provide the constant DC supply of 5 volts, which is seen in the practical design in the above picture. This design was just to see how effective the LM386 was, because I knew I had to improve it later down the road. As seen in the next slide, there will be a video presentation showcasing the effectiveness of this design.
It took a few decades to roll out, but people really did great things there. And they developed other kinds of principles that didn't exist before, like from chemistry to chemistry. It's a big gap, right? And those principles are what we should be thinking about right now. So, can you imagine a chemist saying, "We need to create this field called..."
That video showed you the beta version of our amplifier.
In order to reduce the noise heard from the LM386 design, it was chosen by me to create a discrete audio amplifier. After further research and discussion with the professor, it was concluded that Class AB driver state circuit, as shown on the bottom right with the schematic, is the best option to reduce the noise heard with the LM386 design. The diodes within the schematic provide the 1.4 voltage drop needed to reduce the crossover distortion greatly at zero. With this reduced crossover distortion, essentially the output can match the input signal with little to no difference except for amplification. Because of this, the noise also reduces. As discussed on the report, several calculations were made in order to come up with the final resistor and capacitor values for the schematic shown in the previous slide. Once the schematic was approved by the professor, several simulations were ran in order to ensure the amplifier worked at different frequencies. As a result, from 1K to 5K frequencies were tested. And in this slide, I have provided the results for the 1K and 2K respectively. And as you can see in both of the pictures, the blue signal, which is the output, is almost identical to the green signal, and there is little to no crossover distortion. As a result, I knew that this design would eliminate the noise issue that we had with the LM386. But due to time constraints, we weren't able to implement this design and we stuck with the old LM386 design.
To conclude this video, Kasim will show you the product he worked on over the course of 545 hours building Preventiv.
Hey, how's it going? In this video, I'd like to share how I managed to build Preventiv from scratch in just under 5 weeks. Preventiv is a contact tracing app for COVID-19. Think about its application in the following way. Let's say you're going out to get some groceries and someone you come under contact with is potentially infected with COVID-19. What Preventiv does is it alerts you that someone you recently came under contact with or someone you are currently under contact with has been exposed to COVID-19 or is displaying symptoms off of it. This enables you to intelligently social distance yourselves when social distancing is not feasible at all times. Another example of Preventiv is when, let's say you and I come into contact with someone today, and a week from now, that very person is tested positive with COVID-19. What happens is you get notified from the app saying that someone you just came under contact with in the past 14 days has been tested positive with COVID-19. This enables you to outsmart the virus by predicting the hot spots of virus and approaching the tree graph from a totally different perspective, and this way we can exponentially curb the spread of the virus, slow down the spread of the virus. And the question you might ask yourself is, how did one teenager build this app which delivers this promise when there were other companies such as Google, Apple, and institutions such as MIT, Stanford, and even governments such as Singapore, Taiwan, Australia building similar services? So it all comes down to the core fundamental technology, the proprietary technology under this whole suite of applications is Bluetooth, specifically Bluetooth Low Energy.
There are two types of Bluetooth services: classical Bluetooth and Bluetooth Low Energy. You can think about classical Bluetooth as connecting where a user, you and I, are asked for permission to connect to a device. So when you connect your headphones, such as these, to your phone, it uses a classical Bluetooth, which requires active permission granted from the user. But when it comes to Bluetooth Low Energy, it's different. It's different in two ways. The first, as the name itself, it uses less energy as compared to classical Bluetooth devices. And and this is particularly important because when you're scanning for nearby devices, you don't want to use up your phone's battery power, because that will drain away your phone's battery power, and it's not really the incentive of an end user to really use that product, because at what cost is my battery important to my health? Well, it sounds absurd to think about it that way, but really you need to make a trade-off between your phone's battery and your nearby intelligence. And another reason where Bluetooth Low Energy differs is you don't need to seek the permission from a user to connect to another BLE capable device. It's based around this whole idea of a generic attribute service created by the Bluetooth community, I believe back in 2014. I could be wrong. Excuse me. The Bluetooth Low Energy is based upon this idea of a GATT service. A GATT, or a generic attribute profile, is essentially an abstraction layer onto the main hardware, which is the core Bluetooth technology. And a GATT service is a profile. It's basically like an API, an abstraction layer. And it's split up into two parts: a profile and some characteristics. A profile, a service, and some characteristics. And then you have another service, and so on and so forth. So you can think about it in this perspective. At the parent root level, you have a profile. And right underneath a profile, you have a service that your device needs to cooperate with. And this service is determined by a very specific universal unique ID, or a UUID. And this need not be SIG conformed. You can create your own UUIDs, but they have to be unique in the sense that you cannot have two service IDs with the same UUID, because it results in ambiguity. And underneath your service, you have basically a set of characteristics, or an array of key value pairs. And that's essentially what the underlying principle behind a GATT service really is. So what ends up happening in a GATT service is the following. Well, before I do that, why do we need Bluetooth Low Energy? I hope you understand why. If not, the reasons are it uses less power, so saves more, saves battery life, efficient for the end user. Doesn't need to connect to other devices, critical, because if you're trying to scan for nearby devices and connect to them and retrieve information after you connect to them, well, you want to make sure that's as passive as possible with very little or minimal user interference. And that's why BLE is powerful. And why do we need BLE? Why do contact tracing apps that you hear about these days use BLEs? The reason for why they're using Bluetooth is because it creates this idea of a decentralized meshnet, a decentralized version of collecting data. And the reason why it's decentralized is because Bluetooth, as you know, is based on a relative radius to the person operating it. If it was a GPS-based location service, for contact tracing, that's what MIT did earlier. It's through their private kit app. They use GPS, but that was based on a central location. You know, they have a server at a central location with a central database, and that's taking out your GPS data. But if you have a Bluetooth-based application, every client, every user becomes the master itself. Therefore, every user is a decentralized user. It takes away the control from a central source and brings it to each individual user itself. That's what makes Bluetooth a centralized way of communicate, a decentralized way of communication, while GPS-based applications a centralized way, because they communicate to the same satellite, connected to the server, and the server is the same shared across all devices. So the main developer or the main organization in control of the server have access to everyone's information, and that is critically important piece of information that separates BLE, Bluetooth-based services, with GPS-based services, you know, the extent of privacy. Now you can morph them together to get a balance or to get an even more powerful application, and that's exactly what Preventiv does. Preventiv uses the best of both Bluetooth and GPS to create an even more powerful, empowering user experience, not just for the consumers ourselves, but for the overall society in terms of the overall reach and impact for every individual user based on the marginal gain. So, how does Preventiv work? Well, what happens is you have your cell phone and some other cell phone nearby you comes under contact with this phone. We define contact as a minimum exposure time of 10 seconds in a vicinity of your Bluetooth device. Now there are different types of Bluetooth depending upon your classes. So there's class A, class B, I believe it goes to class D, I'm not too sure. Correct me on that. And they depend upon the range that they can transmit data with. Smartphones like, let's see. Smartphones like this one transmits data to about 25 meters in the open environment, and if you get in a closed compact region, it goes up to 5 meters. And this is Class A Bluetooth. And each Bluetooth device gives out several pieces of information of particular interest to the end user, such as an RSSI value, or a receivable. Sorry, I don't remember what it stood for, but it's essentially the signal strength. Receivable signal strength identifier, I'm not too sure. But it basically shows you the power, the strength of the signal it's sending data to all its clients, to all other users. And an RSSI is very important in measuring the proximity of two nearby Bluetooth devices. The RSSI can be calculated by, let's see. So the formula that's being used is is 10 to the power of the RSSI at 1 meter, it's in decibel per decade, minus the current RSSI, and I believe that over, can't remember the formula, just give me 1 second. Sorry. So the RSSI, or sorry, the proximity between two Bluetooth devices can be characterized by 10 to the power of RSSI at 1 meter in dB minus the current RSSI projected by the device divided by 10 times n. N represents the Bluetooth class level based on the transmission power level which each device gives across. And for a smartphone like this, its TX power level is 1. And usually its RSSI at 1 meter is -84. And it's, if the Bluetooth devices are closer to one another, they have a very small negative RSSI. The farther apart they get, it becomes more and more negative. So using this, you can get the proximity between two devices. And proximity is particularly interesting because the closer two devices are, and the longer they stay under contact with one another, the more risky situations get in terms of contact tracing and social distancing and isolation. But here's how Preventiv works. What happens is all devices have, with the given app across Apple, iOS, and Android, have the same shared UUID. The service ID is the same across all devices because that's how we're filtering across all devices. We're making sure that if a given device with a particular service ID exists, that means that device has our app installed. And now that it has our app installed, we can collect some information from that device, and all of this is stored locally, so no server is ever in contact with any of this personal information. And we'll talk about how we're generating this information because it's all hashed and it's all randomized. And all this information is of particular interest to each individual device. What happens is, upon the first installation, each phone generates a complete random, unique UUID. And what happens is it projects its UUID onto every single nearby peripheral, and it advertises. So it advertises its data. By advertising its data, it only sends out its last 10 characters of its UUID to all nearby devices as a byte array through a buffer stream. And it sends it to all these nearby devices. So now, when you have this another phone which has the app installed, it receives that 10 digits of UUID data, and it checks across its own local storage. Once again, local, not global. Checks against its local storage, and if that UUID doesn't exist, then given that it matches the same service ID stored, predetermined when the app was first developed, what happens is it takes up that information and then it stores it onto this phone's information as a potential connection. Now, this phone also transmits a Boolean, a 1 or a 0, saying whether or not it's infected. A 0, false, a 1, yes. And it does so every 10 seconds. So this phone sends out to every single phone nearby, given that Bluetooth scanning is enabled, and the user has a right to whenever to switch it off or turn it on. And what happens is, as soon as you enable Bluetooth sensing, it sends out its last 10 digits of its UUID and a 1 or a 0 signaling if it's infected or not. And this phone receives that information and checks across its local storage, which gets updated every 14 days because that's the period of how long the virus lasts usually for a person, regardless if they're asymptomatic or not. And it takes that information and then it checks across the local storage to see if it is present. If it is present, it doesn't do anything about it, because you already made contact with that person. But if it's not, it stores it, and it also checks if that person is infected. Now, if that person is infected, it would alert itself by a notification through a foreground service. And that foreground service translates to a notification, as mentioned earlier, which goes to the user such that they can, get alerted. And that is first-based contact tracing in a nutshell. Now, how does this work, you may ask? Well, it's quite simple. Which, I don't know why it took Singapore 8 weeks and 40 engineers to do it. It's not that hard. Here's what happens. You have a generic attribute profile, right? We talked about that. You have this smartphone, and you have other smartphones. What happens is this phone that's sending data becomes the slave, and every other phone becomes the master. The slave sends its information to every single master, and it switches from being a slave to a master every now and then. It does it simultaneously, technically speaking, because it's worked on multi-threaded processes. Similarly, this one also sends data and also receives data, and it does so seamlessly, such that there's minimal distortions in events, like loss of connection or something like that. While it's Bluetooth, so it's different story. But what happens is you have this idea of a peripheral and a central device. So there are two types of devices: a central device and a peripheral device. A central device would be your slave, which sends information to every single device. A peripheral is a device you like to send information to. And so they switch back from central, peripheral, simultaneously. And that's basically how BLE data sent through BLE is primarily done. So that's basically how Preventiv works. We have other features such as an nth degree type connection, where we limited it as a hierarchical approach to fourth degree. What that means is, suppose me, A, came under contact with person B. Tomorrow, person B comes under contact with person C. Person C comes under contact with person D. Now, let's say on day number 7, I am tested positive for COVID-19. I go onto the app and update my information. And as soon as I update my information, my connection, so every single person I came into contact with in the past 14 days, is notified. So if you look at it from a tree-based approach, here I am, and it's just all one level. So all my children are leaves, and they're edges. So, and obviously it's not it's not a heap or anything. It's not it's not binary in any sort. It's multi-level, multivariate essentially, and you have multiple leaves. And let's say before I met B, I met A prime, A double prime, A triple prime, so on and so forth. Let's label it such. And on a given day I met B, and then a day afterwards I met, let's say, a person called A 9 prime. It's arbitrarily chosen. So these are my direct connections. Now you know that this connection leads to another tree. Essentially, this one is a node of its own. And now in this case, my children are nodes, and the nodes have their own children, and it depends upon if that children is a leaf node or if that children has another branch to it. So it could be like this, where this connection also came into contact with several people in the past 14 days, or it could be like a null node where it leads to null, nothing, right? So that's fairly obvious. It's just how people interact with. Okay, so let's say person B is our person of interest. So now that I'm infected, I notify every single one of my connections. How I do that? Firestore, and I'll talk about that in a bit. So I instantly notify all my connections, And B is one of my connections. So B gets notified. He gets an alert on his phone saying that someone you came into contact with in the past 2 weeks has been tested positive with COVID-19. Distance yourself. So, in that case, what happens is we repeat this cycle. This is critical to Preventiv, which no other app has developed. Preventiv, what happens is it performs this cycle again, but now from its children. So now every child does the same thing it did with a parent. It gets its direct listings, and then it notifies its children. And the child of B is C, and B notifies its children. So therefore, C gets notified from a connection off a connection. And this is critically important in really curbing the spread of the virus. Because the virus, the R naught of COVID-19, I believe, is around 1.9 to 2.3. And the R naught is relatively low as compared to other diseases such as, or viruses such as Ebola, which had a much higher, I believe 3 to 4, and measles, which had roughly 14. And it doubles every it doubles potentially every 2 days, in certain countries. And instead of limiting your connection to just first degree based connections, which is from here to here, if you build up to multivariate connections, you can really track the spread of the virus at an instant given of time. And this is particularly important to our safety. And in that case, B notifies C. C has connected with D, and let's say this is D, and D gets notified from C. So in this case, a person who happened to be an asymptomatic carrier of COVID-19 has now been tested positive, and that person notifies his direct connections, and his direct connection notifies his direct connections, and her direct connections notified her direct connections, and so on and so forth, up to a certain degree, because it certainly loses effectiveness the more connections you go down under, right? And this is what separates Preventiv, or one of the features that make Preventiv unique. And now you may be wondering, how exactly does this work? Well, I'm glad you asked that question. If you didn't, I really hope you did. Think about it, or now, touche, I'm just going to answer it anyways. So, here's what happens. We have a Firestore. This is where we use a central database. Yes, we have to, because we're morphing out the beauty of a GPS-based service with the beauty of privacy, decentralized, differential, privacy-based, blah, 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 version of Bluetooth. What we have is a central database. And this central database hosts one or two particular pieces of information, one of them being this thing called hashes. Hashes is this collection of key value pairs of the last 10 UUIDs of infected people who went from non-infected to infected. Remember that every phone has a local storage, and in its local storage, it is aware of every single connection it came under contact with in the past 14 days based on its last 10 digits of its UUID. And that is a hex value, so the probability that it's a unique value is 14 to the 10. It's a pretty big number, and getting two devices with the same UUIDs is fairly fair to say that it's impossible. It's relatively impossible. Yeah. So let's say a UUID ended with E76 and AF7. These are the terminating characters of certain UUIDs. Let's say this person's UUID ends with AB8. These are random. And what happens is, once this person goes from negative, it's safe, it's fine, now it starts to develop symptoms. Oh, now it gets tested, it's positively tested, and now a person has definitively proof that it has a virus. And now the second it goes to positive, it uploads its 10 digits of its UUID to Firebase. And now it stores the last 10 digits of its UUID onto Firebase, and every 5 minutes, the foreground service running behind your phone also
for Bluetooth scanning also runs a function which checks if one of the hashes onto the Firestore database is one of my connections. And if it is one of my connections, that means I came under contact with that person in the past 14 days. Therefore, I was under impact or under contact with someone who potentially had the virus or has the virus now. And that's how the notification process works. But it also sends another piece of information, connection level. Not only does this send the last 10 digits of my UUID, but also an nth degree level, starting from 0, or the, when you're going from negative to positive in the app, there is no connection, it's just you. But your connections are the first connections. You yourself are 0, and your connections look at that and do the same thing. So now they send their UUIDs that they came under contact with someone who had the virus, and that one goes up, but it increments the nth degree that they received. In this case, it received a 0, now it receives a 1.